Alright, in this video I'm going to crash course you on an Atwoods machine, and an Atwoods machine is exactly what's shown in the picture. You have a pulley with two objects slung over it where if one object is heavier and you release them, they will accelerate together. And that's the key to all of this, is that they're moving together, they're behaving together. It's a system of objects. And that's the first thing I want to discuss is a system is any two or more objects moving together, whether it be slung over a pulley, whether it be several blocks next to each other when you push one and then they end up moving together. It's all the same, and we're going to treat it all the same. The way we're always going to treat these problems is as a system. We're going to treat them as one single thing moving together. And I think a better way of thinking about a pulley especially is if you have this 4 kilogram object on the left and the 2 kilogram object on the right, we're going to redraw the axes. That's going to be step one whenever you have a system. And we're going to create an axis for the direction of movement. So in this case, our axis of movement, our axis of motion, is going to be along this pathway. So normally we treat X like this and Y like this, but now our axis is bent. It's still the exact same thing. And if you think about it more easily, you can stretch the objects out so that you have the 4 kilogram object on the left, the 2 kilogram object on the right, and we have the force of gravity of the first object on the right and the force of gravity of the second object on the one on the left and two on the right. If we unbend them, FG1 is to the left, FG2 is to the right. And because you know the force of gravity is mass times gravity, then for each of these, the object's weights would be 40 and 20 newtons respectively. And if we apply that up here, we have 40 newtons to the left and 20 newtons to the right. And right there you can see right off the jump the net force for this system, and we're always going to start with FMA. Net force is mass times acceleration, except it's all for the system. So net force of the system is mass of the system times acceleration of the system. So in this case, we'll treat any force that's counterclockwise, or if you're looking up here, any force that's to the left as negative and any force to the right as positive. When you redraw your axis, you should choose, okay, do we want clockwise to be positive or negative? So I'm just going to choose counterclockwise forces to be negative and clockwise forces to be positive because that makes sense in my head. And that translates exactly to what we have drawn over here, whether you prefer to unbend them to make it a little bit easier on your head. And then net force of the system is going to be, well, net force is the sum of all forces, but it's on the system. So we have negative 40 newtons plus 20 newtons. And that's equal to the mass of the system. Well, the mass of the system is the total mass because it's all moving together. So 6 kilograms. And to solve for the acceleration of the system, you just divide negative 20 by 6. And when you do that, you should get negative 3.33, if I'm not mistaken. Give me 1 second. Negative 3.33 meters per second is your acceleration. So it's going to accelerate counterclockwise because we ended up with negative, and we chose negative when we set up our axis system. And anytime you see an Atwoods machine, your thought whenever you get a final answer for your acceleration is going to be, is it less than 10? Because if some object, the 2 kilogram object, is resisting the acceleration of the 4 kilogram object, then the 4 kilogram object has to accelerate less than gravity. So unless there's some extra force that's pulling it down, it should be less than 10. Alright, so that's the basis. Now let me show you a little bit of behind the scenes that we skipped over, add in the details that I kind of cheated through. And we're going to do the exact same problem, except I'm going to add the things that we're missing. So number one, anytime you see two objects attached to each other, your first thought should be, we're setting it up as a system. So number one, the first thing you're going to have to do is redraw your axis of movement. And for us, just like we did in the last problem, I'm going to choose it. Well, this is the direction the motion is going, and I'm going to choose clockwise positive, counterclockwise negative. Step two is label all forces on all objects. So for the left object, we have FG1, the weight of object 1 downward, and tension upward. But wait, we didn't include tension in the previous problem. I'm going to show you why. That's the beautiful thing about systems, is internal forces are always going to cancel each other out. But we're going to continue labeling all forces. For the second object, we have FG2, and we might as well just go ahead and finish the calculation. It is equal to M2G, which is equal to 20 newtons, and FG1 was equal to 40 newtons. And don't forget to label your tension on the second object. So now we've labeled all forces. And 3 is net force, FMA. So your net force of the system is equal to the mass of the system times the acceleration of the system. And no, I don't want to say that yet. So when you do this, all forces that are counterclockwise or would create a counterclockwise spin of the pulley, we're going to treat as negative, and any forces that are clockwise, we're going to treat as positive. So if we look at FG1, it's clearly trying to pull it counterclockwise. So I'm going to assign that as a negative value, because net force is the sum of all other forces, so we have negative 40 newtons. But now we get to tension. Well, tension's pulling clockwise. So we have plus Ft, but now we get to this one. This tension on the second block is trying to pull the system in a counterclockwise direction. If we continued this arrow, it would go up and around, and you would get negative Ft. And then, of course, gravity 2 is going to be clockwise, so it's going to be positive 20. Now, right here we have plus tension and negative tension. Number one, the tension in a rope is always the same. So if you have a block here over a pulley attached to a block, whatever this tension is going to be the same as this tension. Whatever this tension is going to be the same as this tension. They're always going to be the same. And that's the basis for this. But more importantly, they're internal forces. It's block 1 pulling on block 2, or block 1 pushing on block 2. If you were looking at the previous example where we had two blocks next to each other, the force of block A on B is going to be equal to the force of B on A, and internal forces are going to cancel out. That doesn't mean that tension is not acting on block 1 and another tension, the same tension, is also acting on block 2. They definitely are, but when you plug them into this net force for the system equation, they're going to cancel each other out. So internal forces will cancel out when you're in the system, only when you're in the system. And we're going to break that rule in a little bit, or add to that rule in a little bit. But for now, internal forces cancel, which is why I skipped right through that before. And as you get faster with this, you can start to skip that too. But in the beginning, I encourage you to at least put it in so that you don't forget it. And you absolutely have to draw the forces on your free body diagram. That's non-negotiable. You have to draw it. Mass of the system is the mass of every object that's accelerating together. So the net force of the system divided by the mass of the system will give us the acceleration. That's what we're trying to calculate. So the mass of the system is, well, 4 plus 2 times the acceleration, and that's going to collapse to 6, and then we're going to have negative 20 over 6 like we already saw in the previous problem, which is going to give us negative 3.33 meters per second per second. So right there, I just redid the same thing, but I wanted to highlight what happens to those internal forces. Now, we're pretty much done with Atwoods Machines. By the way, Atwoods Machine is just two objects over a pulley. I think I said that in the beginning, but I'm going to reinforce it now. This is half of what you will see on these problems. They'll say, okay, you need the acceleration. And the other half of the object, or the other half of the questions, and they might just give you this question from the jump. Either way, you're still going to always want to start every Atwoods problem with the system. Even if they say, what's the tension force, don't start with this object, start with the system. But if they do ask for an internal force, in this case, tension is our internal force, then if they ask for that, then you're going to start with the system, and then you're going to look at, okay, let's do the net force equation for either object that by itself. So you can do net force for the system and then net force for the individual objects. So for block A, the one on the left, if we look at it, 4 kilograms, and I'm going to keep my same axes where up is positive and down is negative because up went clockwise and down went counterclockwise. So up is positive in this case, so we have tension up and the force of gravity downward. If they said, what is the tension? We need to solve for this internal force. That's why we need to look at the individual object and not the system, because in the system, the internal forces cancel out. So if we create a net force equation for object 1, well, it's going to be the mass of object 1 times the acceleration of object 1. But here's the trick. If they're all accelerating together, the acceleration for object 1 is going to be equal to the acceleration of the system. That's why I say you have to do the system first so that you can get the acceleration and then plug it in for the individual object. Well, in this case, we're going to just plug everything in. Net force is the sum of all forces, so we have positive tension minus the weight equals M1A, which is 4 times negative 3.33. And then we can plug in our weight to solve for tension, so Ft minus 40 equals 4 times 3.33, or 13.3, negative 13.3. And now we're going to add 40 to both sides to get tension by itself, and we're going to find that the tension is equal to 26.7 newtons. But wait, how did you know to choose object 1 or object 2? Well, I already told you tension in the rope is going to be the same everywhere throughout the rope. So let's prove that. Let's look at object 2. And to do that, to find this tension, tension 2, and I'll change colors so that pops a little bit better. For object 2, we're just going to do a net force for object 2. Net force is mass 2 times acceleration 2. Net force is the sum of the forces. Well, we have the force of gravity downward, but keep in mind that's a positive direction because it came from this chosen axis that we had. Clockwise positive, counterclockwise negative. So Fg2 is going to be equal to positive 20 newtons because we chose clockwise as positive, and we still need to solve for tension. Well, net force 2 is going to be Fg2 minus the tension equals M2A. And a negative because that tension is pulling it counterclockwise. So 20 minus tension equals mass 2, which is 2, times A, which is negative 3.33. And I think you people already see this. Negative 6.67 or negative 6.7 equals 20 minus tension. And then with a little bit of algebra, you should find that tension using the right object is also going to be 26.7 newtons. So you're going to get the same tension because tension is the same everywhere throughout the rope. I hope this video helps. I hope it was fast enough that you could follow, but slow, fast enough that you didn't burn time, but slow enough that you could follow. If you do have any questions, please work together. And if you're still stuck, please reach out to me and I'll try to help you. But good luck and have a good day. Bye.